Welcome back, chat. Today we're talking about tides. Okay, so sorry about the restart. Tides are the cyclic rising and falling of sea level, and what I have here is just a fantastic picture of our planet, and we're working with a couple really nice assumptions to simplify this. We're assuming that we have a solid rock planet that's completely covered in water, because continents mess up a whole lot of this as we look at it. It gets way more complex. But a second ago there was another spherical object over here, representing what? The moon. Okay, I'm going to throw the sun on this picture as well. But here's something kind of crazy. What's bigger, the sun or the moon? The sun. By a little or by a lot? By a lot. What pulls harder on our planet? The moon. The moon pulls about 4 times as hard. The gravitational attraction to the moon, way stronger than the sun. Why would that be? It's like 800 times closer. The moon is much, much closer to us than our sun. Okay, as we look at this, the right side of this planet is easy to make sense of, I think. On the right side, what is the responsible force for this attraction? It's called gravity, right? Like the moon is attracted to the earth is attracted to the moon. It has something to do with how much mass there is and the distance between them. Okay, just to mention it, the moon pulls on the earth. Does the earth pull on the moon? Constantly. It's a two-way street. This is gravity. Okay, now, the attraction there is a pretty big idea, and it's not really understood in modern physics, just so you guys know. Gravity, nobody knows exactly how and why it happens. It's big questions left unanswered in physics. Okay, here's the issue, and I've heard a bunch of possible and some pretty good explanations for it. If you were to take the center of mass of our planet, it'd be right in the center of this perfect planet. When the moon pulls on it, what do you think happens with the rock? Like the planet itself. So like if you are going around and I'm pulled toward you there and then you're over here, I get pulled that way, right? Now, what has more mass, water or land? What's heavier? Land by a lot. Which means this attraction with the land is stronger than the attraction with the water, purely due to the masses. Are we cool with that? Gravity pulls harder on the planet itself than it does the water on top of the planet. Now, when this happens, there's a few different little pieces going on here. First thing, when this attraction occurs, my center of mass, the whole rock planet moves. It's like it moves closer to the moon, and that was what you were alluding to. Now, beyond that, gravity depends on distance. That's a true statement, and whether you knew that or not, it's true. Everything in the universe is attracted to everything else via gravity, but there's a lot of stuff in our universe. With that said, our planet's kind of big. If you look at the right side of this picture and the left, where does gravity pull harder on our planet? So from the moon, so it does act on the center, but do you think the strength of the moon's attraction is stronger here or all the way on the other side of the planet? Or the same? It's stronger here because the distance is closer. Now, it's not a huge difference, but there is a difference. Now, when this happens, we get this whole planet to move, and the water has way less mass, right? So I'm going to draw a larger picture. You don't have to draw this one. But let's say we had a planet and there was no tides, and it's all the same. Everybody cool with that? Now, pretend that we have a big, massive object called the moon pulling the Earth. Now, the Earth reacts pretty quick to it. At this, we're not going to go into that. But it's almost like this happens. What do you notice about the water's depth on the left side of the planet? When I move from here to now the moon tugs it just a little bit over here. Did this depth get bigger or smaller? This got deeper, right? As I get pulled to the right, there is more water behind me because it lags. The planet can't, it does, but it can't really stretch out, right? It can't elongate. Water can. Now, the difference in gravity between those sides of the planet means that the whole planet gets pulled, but not the whole water. It's not a big solid sphere of water, it's liquid, it can move. Okay, beyond that, when I see this whole planet get pulled sideways, it tells me that, hey, look, this just got deeper, like a high tide, the depth is bigger. What happens to all this water over here, though? That's way closer, so I'm talking about on this side of the planet, that's way closer to the moon. Does it get pulled harder, less hard, or the same as the water over here? Am I losing everybody? Okay. Do you understand the part when I'm moving the planet? Okay, the planet moves, the water stays. We're all good there. Okay, so check it out. Gravity acts less strong here on this water. Like it's not a solid object, but there's less gravitational force on the water on the left side of this picture. Is there more gravitational force than here? On the water here. Is this closer to the moon? Which means all this water gets attracted to the moon. It's close enough that there's a difference and it's noticeable. This water has to pull out here, and they use the word bulge, is what you're going to see everywhere. The water bulges out this way. The water, to be able to increase its depth here, it must have lost some water from somewhere, right? So it pulls it from the poles in this picture. Okay, that's the first little step of this. Water gets pulled near the moon, and it pulls a high tide here. The whole Earth moves, leaves all the water, resulting in another high tide on the other side of the planet. Okay, that's step one. Beyond this, though, there's a few more pieces. This works really nicely when the sun and the moon are on the same side pulling. What's stronger gravitationally? Sun or the moon? To us? The moon, because we're so much closer to it. Okay, I want to consider a different situation. If the sun is here, and this is just a nice little thing, there's my sun. Do we have a new moon, a full moon right now? And I'll formalize this and make it nice in your notes, just so you guys know. We're just building it up right now. Is that a new moon or a full moon? And what's the difference? Do you guys know the phases of the moon? Okay, new moon, right here. Why is this a new moon? Where's it nighttime on that picture? Left side or right side of the planet? Are you sure? Here's the light leaving the sun. So it's day over here. Right? Everybody okay with that? Which means it's dark over here. Can they see the moon on this side of the planet? So it's like there's no moon in the sky, but the moon's not gone, it's just hidden. This is your new moon. Okay. What's changing as we go through time with regard to the Earth, the moon, and the sun? What's the Earth constantly doing? Spinning. Now, the centrifugal force, the reason I asked Crystal about this is a centrifuge. If you need to separate blood and plasma, or red blood cells and plasma, you just spin it really fast on a centrifuge. That's why I was thinking that you might know that word, but I don't know how much we do that in the clinic. Little devices, they just spin really fast. Okay, centrifugal force, when you spin something, you get pulled out, right? You've ever ridden on a merry-go-round, it's like you're getting thrown off. Okay, only because you're moving. That's the only thing that causes it. Now it does cause that water to push out near the equator specifically. These movements and centrifugal forces are enough to impact our water, at least to a small degree. Where I'm starting to wonder about, though, is this picture, I think, hopefully makes sense to how this works. What if the sun was over here instead? What changed about daylight on our planet that was here? What side's in the daylight now if this is the sun? The left. Here's my daylight, and I'm just going to do some light overlap here. That's all daylight right there. That half of the planet's in the sun. Is this a new moon or a full moon? That's a full moon, because you can't tell in this picture because it looks like it's being blocked, like you'd get an eclipse onto the moon, but it's not really what's happening. The moon does some crazy stuff as we're going. We're not in a physics class. Okay, the moon would be illuminated by the sun. Would these tides still live like this? Would it still be high on both sides of the planet, even if the moon and the sun were fighting on opposite sides? Think so? Other thoughts? Would it still be just the high tides here and here?
The tide would be higher on the sun's side if the Earth.
Okay, so obviously there's some bigger pieces going on here, right? Here's the crazy thing, equally high. Whether the sun and moon are in line on the same side of the planet or on opposite sides, you get the same high tides and low tides. Like, essentially no change. Now, beyond this, we're going to look at seeing if we can't get a nice generalized way to describe this. With the continents, that flow of water gets harder. It gets restricted. You have to move in different places. Might have an explanation for maybe why seas get rougher in certain places of the planet. Okay, how do we generalize this in a nice, easy to explain way? I know how I want to do it. How would you explain it if I said, go home and explain how the tides work and why we have high tides at opposite sides of the planet? Could you explain it to somebody right now? Work it out. At each of your tables, I'm going to make, in your words, spend a couple minutes. I want you to explain this to me. I know that I understand it. Show me that you do. Cool. Physically write something down. You guys can take turns writing. That's fine with me. I want you to write a short explanation of why there's high tides on opposite sides. In your words, what did we just talk about? Let me. Oh, up there. Okay. I thought it was. After researching these things, guys, for those of you watching, the last few minutes of class, I know the video is really short. It's like last 20 minutes of class was researching how this works. But beyond that, also, your task is in 3 to 5 sentences, explain why there are high tides on opposite sides of the planet. I want you to write this as though you're explaining it to a 5th grader. If you're watching this video, go ahead and just shoot me an email with it. I'm fine with it. Cool. Good luck tonight if you're watching this video before. If not, I hope you won. Either way, go Raiders.